All right, so this is part two of our system stuff, really a review, because this is a pretty popular topic for those of you who've had, we've all had Algebra 2, but even in Algebra 1. So the substitution stuff, what you want to do is you start with any place you can easily isolate one of the variables, and is a great place for substitution. So in this one, y is already by itself in that top equation. When we say substitute, it means to replace a variable in the other equation with the contents of, like, for instance, y equals 2x minus 9, so it replaces the y in the other equation. And make sure you use parentheses, because parentheses are to capture if there's any coefficient with that y or a negative, like we're seeing here. You have to distribute it to everything that's in that parenthesis during substitution. So we've got that. So there's that negative being distributed. In the end, just take your time. One step at a time is the best way with algebra, because you know there's errors you can make, and the experienced algebra folks know that you just show all the steps and you're likely to cut back on error if you do so. And then if I clean this up a little bit, here's some of the details. You know, you got to get the x's together on one side and the numbers on the other. So it looks like we add 2x to both sides here, and then ultimately you're going to get x by itself. And when you have negatives on both sides, you can cancel them out. Basically divide both sides by -1. And we get x equals 6. That's part of the story. A system means find all variables, the values of all of them that satisfy both equations simultaneously. And we need a y that goes with this. Either equation is fine, but certainly that first one with 2 times x minus 9 is the easiest one. So put 6 in for x. That'd give you 12 minus 9. And that's a total of 3 for the y, 6 for the x. If you need to write the coordinate point, because remember this is about, if you graph it as an intersection point, so the coordinate would be 6, 3. Okay, next one. This one's a little different. You want to isolate a variable it's not already isolated, and then sub it into the other equation. So when I get to that piece, you're going to isolate your favorite variable. You know, doesn't matter which one it is. I went to the bottom equation to isolate because it just seemed like it was easier in that bottom equation to get x by itself. There's no rule about which one you choose. It's really your elective. And then if I take that 10 minus 8y, put it in for x in the other equation, and then distribute the -3 that's in front of it very carefully in the parentheses, this is what I get. Anytime this video is too fast, you know you can do pause, back up. That's the best thing about videos. So don't be shy with the play control buttons while you're doing this. And then to the next piece, you can combine like terms. Of course, getting y by itself is the key. So I'm going to isolate it by getting rid of those -30s. Add 30 to both sides. It cancels to 0. That's not a bad thing. And then divide both sides by 23, and it's still 0. 0 divided by 23 is 0. Halfway there, we got y equals 0. Find whatever equation you like of the originals to put that y back in. Solve for x. I took the top one there just for fun. Put in 0 for y, then you get -3x is -30. Divide by -3 on both sides, you get 10. So coordinate would be 10, 0. If we graphed it, we'd find an intersection right there on the, would that be the x-axis, 10, 0. On the next page, or the next piece, there's elimination. So substitution, fun one, works really well for a lot of systems. In fact, it's very powerful. We use it when we get to nonlinear systems, things that have squareds and cubes and beyond, or natural log, etc. But now with the elimination, anytime you have a nicely lined up x's and y's, or you can get the x's and y's lined up easily, and by the way, it's not just lining up x and y's, it's also lining up the equal signs. So we don't ever want to forget this is part of it too, lining up the equal signs. The second one, the second equation, just take note of it right here. Notice these aren't lined up, those equal signs. That's going to be something we're going to want to fix when we get there. So first things first, that first one, I need to get, this is the rule of elimination. You want to have opposites in those lined up variables above and below each other. So for instance, I would like to see a -8y below that positive 8y in the top equation. So when I add them together, so elimination is multiplying a row by a number, or rows, you can do both rows, can get multiplied, and such that when you add the two equations together, you cancel out a variable or variables. And if I multiply the bottom equation by -8, when I add the top equation to it, the y's will cancel. And I'm sure that's something that you remember. So here are the equations rewritten. I've multiplied the bottom equation by -8. So when I add them together, right now those 8y and positive 8y and -8y will cancel. So the result is a negative 34x, no y's, which you can leave blank, by the way, and negative 136. And then I need to divide both sides by negative 34 to get the x alone after that. But that 0y really does mean 0. I just wrote it there for emphasis. But if I divide by negative 34, we get 4. So there's my x. And just like before, we need to plug that x back in to get y, the other variable. Choose your favorite equation. I chose the bottom one. And if you take that on, we put 4 in for x in the bottom equation. It looks like we get 12 plus y is 15. And then if we subtract 12, we get y is 3. So 4, 3, our coordinate point of intersection, should I graph those? Okay, next one. Now, the next one, like I said, we have to line up those variables. So that bottom equation, if I subtract 2y from both sides, then everything is going to work out. So that's now lined up. Equal signs, variables, both have to be lined up. This is a precursor to matrices where we have to do the same thing. You line up all your variables and equal signs before you apply matrix rules, which are basically elimination rules to get to a solution of a larger system of equations. So keep this all in mind. This is all skills. Even substitution is all part of the whole process of solving matrices. Okay, so now we're lined up, ready to rumble. It looks like we have opposites in the y's already. Good deal. When we add those together, we get 11x is 33. If we divide both sides by 11, then we end up with x is 3. So that's a nice start. But the y comes from subbing it back in as always. And then we find out y happens to be 4. And if we put that together, that's 3, 4 is the coordinate point of intersection. And we're off again. So pause as needed, but I'm going to keep cruising. Here's a final equation to do by systems elimination method. And this one's a little different because I can't multiply a single row by a number. I could. It would have to be a fraction. So I could multiply the top by some kind of fraction that makes that like, I don't know, I can multiply by negative 4 or 5/4 on the top so that I can have opposites in my x category. But if you want to avoid fractions, and I love fractions, so no reason to do that, but if you want to, you can also choose this option, multiply one row by a certain number and another row by another so that you get opposites, in this case 5 on top and negative 4 on the bottom. There are other combinations that work, so this isn't the only way. But when you do add these together, the x's cancel. The y's end up negative 3y is negative 15. Therefore, dividing by negative 3 on both sides, y is 5. Put it back in. We got x pending. And if we put it back in, we find out that, let's see, divide both sides by negative 4. We got 6. X is 6. So there's our coordinate point solution, just a little bit different. Had to multiply both rows by something, a really cool option if you need that. And you can do that anytime you like. Okay. So sometimes in systems, the solutions are not singular x and y values. We get other scenarios as well, special cases. There's no prescription on what type of solving you should be doing here. So choose your favorite method. The first one kind of lends itself to substitution because that x is all by itself. So I tend to choose that. Whoops, got to go back a page. So if I hit, yep, there we go. Hang on. I got to find my way back to where I was. There we go. Get my slides in order. There we are, and done. So when you do that special case, you just do substitution to make that happen. So I'm going to work quickly on this one. Looks like I lost my pretty print. But 2 with the 12 minus 3y replacing the x that was there, plus 6y is 24. That's all set up. I'm going to distribute my 2, of course, and get 24 minus 6y plus 6y. That's interesting. It's 24. That little scenario there is interesting because these cancel, and what we're left with is 24 equals 24, which of course is always true. This is an instance of there are actually infinite solutions in this system, and that means if we're talking intersection in the graph, it has infinite intersections, and these are lines, and if lines infinitely intersect, that means they are the same line. They overlap. These are overlapping lines, so infinite solutions in this scenario. When you get to the same number equal to the same number of any kind, that's the case of infinite solutions. The next one, you're probably already anticipating what's going to happen in this one. I think I'm going to go with elimination and multiply by, negative 2 on top. And if I do that, then I get negative 6x, I'll just write it here, and negative 4y, and negative 20. Okay, that's my top equation redone. And then you add them together, I get, wow, a lot of cancellation. I get 0 equals, what, 10? So when that happens, obviously that's not true. So what happens, this is a no solution case, no intersections that take place. And that's one of those where these are parallel lines that are never going to intersect. They're not going to have any solution. So think of intersections in the graphical sense as a solution. In this case, they don't have any. Cool? So that's round 1. I will finish up the other parts of this. So that's all the by hand work. The next thing is we're going to get into nonlinear solving by hand, and then we'll also do graphing. And that'll be part, 3, I think? So far, so good.